So what should I do to bring it here?
So what are you using? PDF?
It's in PDF, right?
Do you know how to do this? The PDF program?
There's a way to mirror, or you have to just to move it like that. It's just kind of control. Oh, here you go. Yeah, I saw that you did something. Oh, okay. Hello, everyone. I'm Nima Nouri from Yale University School of Medicine, where I'm doing my postdoc training in the Kleinstein lab, and I'm going to discuss today the methodology that we have developed to infer the clonal inference from high-throughput B-cell repertoire sequencing data using a spectral cross-chain based method. Just the outline of the talk, I first discuss the type of the data we play with it, namely we call it B-cell repertoire. Then I will discuss what is the definition of clone, what we call it as a clone, and then I will introduce two different methodologies that we have developed to infer the clone relationship, namely hierarchical-based clustering-based method and also a spectral clustering-based method. So I will refer hereafter as HC and scope. And then at the end, I will present some results to compare this methodology. Okay, what is the B-cell repertoire? The abbreviation is the BCR here, and then the last, I guess, doesn't work anymore. Just maybe this one works. Okay, this one. Okay, so a B-cell repertoire is a collection of all unique receptors in an individual. Here I'm showing you an infographic of the B-cell receptor, technically immunoglobulin molecules, which contains two main subunits. The first one is the heavy chain, and another subunit is the unit chain. For inference to clonal relationship, we focus on the heavy chain. Heavy chain I'm showing you here, which basically has been made by 4 different sections: the constant region, the joining region, the diversity region, and the variable region. And the segment that connect these two, diversity and joining region, we call it junction segment, junction region. I'm going to discuss how I use all of this information to infer the clonal relationship between B-cell clones. Thanks to the next generation sequencing data, rapid improvement in this technology been able us to analyze these B-cell repertoires. These data are sampled, in the wet lab, and they will pass through the protocol of the next generation sequencing and produce the data, and it comes to my desk. So when I get the data, I will see something like that. A repertoire can contain about 1 million sequence, less or more, and I just have a raw data of the characters of the ACGTs. So we have developed several toolkits and softwares to perform the pre-processing and the quality control check of this data set. So after a lot of layers of the pre-processing, we tabulate in this data and analyze this data, and we become very organized shape of the table. You can see here, for example, each row is represented of the one sequence, and each column is the information corresponding that particular sequence. For example, we provide the information about the V genotyping, about the J genotyping, and also junction length, junction is so far. All the information is being included in this table. So okay, the goal is we take this table, and then we try to infer the clonal families. What is the clone? First of all, what's the motivation of this work? Clonal family inference, we call it clonal family inference problem, is the fundamental unit of the B-cell repertoire analysis. Every underlying analysis of the B-cell repertoire needs to know about the clonal relationship between all these sequences B-cell repertoires. What is a clone? Clone is a group of B cells that share an ancestor, germline, but have different sequences. So for example, I'm showing you a sequence of a clone which contains several cells. These cells through the cell division, and during the cell division and also affinity maturation, they go through the somatic hypermutations. So the sequences are different, but we believe that all of them are somehow related to the germline, to the sequence, to the same ancestor. So the goal is we take this tabulated data, and then we use the methodology that we have developed, and then we add this one column here as a clone identifier. We say that, okay, these sequences are somehow related and belong to the one clone. Okay, how do we refer these clones? Cloning is performed based on the sequence similarity. So which sequence are more similar or less similar? To find that, we use all the entire nucleotide sequence is used for clonal relationship inference. We use all the VGen information all the segments that I discussed. So the cloning recipe is well established, as well known. it has two states. The first state is just a categorical grouping, which means that we just partition sequences first. At the first stage, we partition all the sequences to the groups of sequences that share the same V gene, J gene, and junction length. Okay? And inside of that, each group, we leverage the high diversity of the junction region as a fingerprint that sequences are clonally related. Okay, so this is the main step, and then we develop techniques to perform these two steps. Okay, the first method that I'm going to discuss is cloning assignment using hierarchical clustering based technique, HC. So again, this process contains 5 main steps. The first step, as I said, we group them with same V gene, J gene, junction region, and then inside of each group, we perform a similarity measure using Hamming distance between the pairs of the junction sequence in each group. I said that the sequences are the same junction region length, they have been aligned, and then we just perform the Hamming distance to measure the similarity. And then we perform hierarchical clustering over all the sequences inside of each group, and then we just need to find a threshold to cut the tree and then find the clonal relationship between them. So how we find that this threshold is the challenge. We use the distance to nearest distribution to find this threshold. Distance to nearest distribution is that inside of each group, we calculate the distance from each sequence to all the rest of the sequences in that group. We dump all the data to the histogram, and that histogram is typically bimodal. That first mode represents the sequences that are clonally related, and second mode represents those sequences that are not clonally related, namely the singletons. And then the threshold would be the vertical line that separates these two modes. We use that threshold, and then we cut it, and then we decide which sequences are clonally related. However, we developed methodology to optimize what's the best threshold. We are using fixed threshold. We don't know what is that, so we have developed a methodology to find the optimized fixed threshold. I use this distance to nearest distribution as a benchmark to test all my thresholds. So I just tune the threshold, and then I will perform some check to find out which threshold is the best. I use that distance to nearest as the receiver operating characteristic. I calculate the sensitivity and the specificity for different thresholds. I use the mixture method to fit both modes, and then I calculate the integral, the area under this case, calculate the sensitivity and the specificity of that particular threshold. I average that, and wherever that threshold maximizes this formula, that would be my optimized threshold. We have done a lot of benchmark studies to back up this claim. This result will be published soon in Frontiers in Immunology. And then we take that threshold and simply use the clone inference. Although we are using the optimized threshold, but it is a still fixed threshold, it's not the best scenario. There are 2 challenges that may be problematic for us. First of all, fixed threshold does not allow cloning for widely varying levels of clone diversification. We better, instead of using a fixed threshold for all of the sequences, it's always better to focus locally on the local relationship and find which sequences are really close to each other. And also the second challenges that we are facing, it's that distance to nearest, it's not always guaranteed to bimodal. So if we are failing to bimodality, for example, some experimental here and some simulated data, you can see distance to nearest distribution is not clonal related. For example, blood samples usually are highly clonally expanded, so all of the sequences are close to each other, so it would be very hard to find the threshold. So because of these 2 reasons, we had to develop new technique, which instead of using the fixed threshold, we are developing the technology to perform adaptive threshold, but we call it a scope. What does a scope stands for? It's just abbreviation, we made it up. A spectral clustering for clone partitioning. And then spectral clustering is, as I'm pretty sure you know, is a well-established and well-known methodology. It has 3 different main stages. Then if you have, for example, a data set, we calculate the affinity maturation matrix. The affinity maturation matrix determines which sequence, how these sequences are close to each other or far away from each other. It's kind of weighted matrix. And then from that affinity matrix, we calculate the Laplacian of that matrix. From that Laplacian, we eigendecompose that Laplacian matrix, calculate the eigenvectors and eigenvalue, and we simply perform the K-mean clustering and standard clustering technique to define which sequences are clonally related or not. So all of the story is just a 3 main stage. The key engine here, how we calculate the affinity maturation. As well as we can better calculate the affinity maturation, our result would be more accurate. Okay, we use the Gaussian kernel function to calculate that affinity matrix. The kernel Gaussian function will provide us a fully connected network among all the sequences. that affinity matrix would be symmetric. And the values, the element of the matrix would be between 0 to 1. The 0 means that those sequences are far from each other, and the probability of these sequences belonging to the same clone is low. And 1 is when these sequences are very similar to each other, the probability of being this part of the clone is very high. However, the exponential term here has a two section, numerator and denominator. The numerator is simply Hamming distance. We calculate the Hamming distance. I again emphasize we have junction region the same length, so we can use the Hamming distance. If you have the junction region with different length, you can substitute with the Levenshtein distance. The denominator is a very important part which decides which sequence, which weight this relationship. We need to find the local relationship between sequences. So usually, if you look at the literature, they use the fixed standard deviation for this local neighborhood. The way we did, we make it a little smarter and also unsupervised. We calculate these scale parameters for each sequences instead of using the same standard deviation scale parameters for all the sequences. How do we do that? The idea is that, as I said, we calculate the standard deviation for each sequence. I calculate for each sequence, I will make this rank table as of all the distances from that sequence, and then the standard deviation of all the sequences that fall under that first gap would be my scale parameter, particularly for that sequences. So I calculate these scale parameter for all the sequences. I make these affinity matrix. I will decompose it. I will calculate the eigenvalue and eigenvectors, eigenfunctions, and then I will perform the k-mean or k-mean clustering technique, and I just decide this clonal inference. So this is the key engine of the key part of this methodology. Okay, some results. Okay, so to test it, we needed to have some simulated data. So we use some published simulated data. We generated 40 simulated data published by Gupta et al. 2017. And the key point about this simulated data is that because it's simulated, we know the clonal relationship. So we can perform the methodology on top of this data, and then we test the performance of our clustering. So I've calculated, we have performed the hierarchical clustering, also a scope over all these sequences. You can see the diamond is the hierarchical clustering, and the circle is the scope. And we calculated the sensitivity and specificity of this technique. To zeroth order, you can say that both of these techniques performs fairly well. However, we tested for different junction region. You can see that in the short junction region, we have variation, and we have a lot of false positive and false negative. The reason is that the short junction, you don't have enough information because these are very short. In country, when you have the longer junction, you have more diversity, you have more information to use. Okay, how we can test this methodology on the experimental data? So experimental data, we don't know what's the clonal ratio, so there is no way to test it. But we believe that the true clones have more shared mutation. So we count these shared mutation, and the higher number of the shared mutation indicates better clonal inference performance. These shared mutations are those mutations that happen early of the cell division, so believe that it would be repeated all over the affinity maturations, that will it would be conservative, so more shared mutation means for us better cloning. Okay, here I'm discussing what's the shared mutation. If I consider the first row as a germ line, the shared mutation is the mutation that happen on all the sequences. For example, we have this one here and we have this one here. We have two shared mutations. It's supposed to be check mark. And then here, for example, it's not shared mutation. Some of the sequences had this mutation, and some of the sequence has a different mutation. So totally for this sequence, we have, for example, two shared mutations. The key point here is that we don't count the shared mutation in junction region, because as I discussed, we are cloning by using junction region. We don't want to be biased by our cloning. So instead of using junction region, we're just focusing on the V region and counted the shared mutation in the V region. So okay, we performed this counting process, the counting mutation over several different experimental data. We mainly used the 58 different subjects with acute dengue virus infection. It was a published paper by Parmesan et al. 2013. So it is 58 different individuals. All these numbers are the subjects. The point is, at the end of the study, most of the cases, both hierarchical cluster and scope performs as same. The shared mutation counts was the same, but every single time that shared mutation are different, you can see that the scope has more shared mutation, counted more shared mutation than a spectral clustering. that which means that a spectral clustering, because it's focused on the local relationship and it's kind of using adaptive threshold instead of using the fixed threshold over all the sequences, the clones are more homogeneous. And the clones are more homogeneous means more shared mutation. If, as an example here, you can see that dendrogram, for example, if the fixed threshold, you're using the 15% of the similarity, but scope is using the shorter junction, a shorter threshold, and technically the one clone which was inferred by the hierarchical clustering will be divided to two different smaller clones which are more similar to each other. So because of that, we are inferring more homogeneous data. So we believe that a scope is working in that case has a better performance, and you're better off to use the adaptive threshold and focus on the local relationship instead of using one single fixed threshold over all the data. It's not the ideal case to do. Okay, another problem that I discussed, another challenge that I discussed we had by the hierarchical clustering was that optimizing the fixed threshold. As I said, not always distance to nearest distribution guaranteed to have the bimodality. So therefore, this is the published simulated data with Ralph Madsen 2016. We are showing a single, the distance to nearest distribution. Here you can see that it's not bimodal. So instead of hierarchical clustering method would be failed. So we use the spectral clustering, and you can see that this is the table of the diagonality. This is the x-axis is the true clonal size, and the y-axis is the inferred clonal size. The diagonality of this shape shows that the performance is better and performed very well. Also, since the clonal relationship is known, we can calculate the sensitivity and the specificity, which is very high. Also, scope has the computation efficient, more efficient than hierarchical clustering. You can see that hierarchical clustering, by increasing the number of the sequences, exponentially increase, while the spectral clustering, for example, for 140,000 sequences, you just need the 20 minutes to infer all the clones. We have developed this function, and it's freely available in incantation website. You can find it and install these tools easily, and we define is the R package base. You can use this define clone scope function. You just pass the data and tune some parameters, and it will pass you the data, which we call it change-based estimate. It's the standards that we use it, and everyone has to use this standard. It will identify your clones, show you the clone identifier. I also developed some function to perform the assessment of this clonal relationship, which give you the effective threshold that you are using instead of the fixed threshold. We show that all the sequences has this effective threshold. Okay, in the summary, partition B-star sequence into clonal group is a key step in the B-star repertoire analysis. A scope addresses the non-biometric challenge in distance to nearest distribution, uses an adaptive threshold to tune the required level of similarity among sequences in different local neighborhoods, provide an accurate identification of the clonal relationship, and also is computationally efficient. There are more mathematical details that I didn't bring it up. There was no time to discuss, but however, you can go to the Proceedings paper which was published. It's online, and look at the details. We are part of the Kleinstein lab. You are welcome to use this package. We have several packages from beginning from the pre-processing of your B-cell repertoire to the analysis, mutation, all. We have developed a lot of tools and user-friendly to use for your analysis. And at the end, I will finish by thank you for your attention, and I open for some question if you have.
We do have time for a few questions.